Alright, so once again, we are starting with the law of Biot-Savart, and this time instead of for a straight current carrying conductor, we want to do this for a circular loop. And we're specifically finding it at the center of the loop. So we have our law of Biot-Savart here, so where we need to do the cross product of dl cross r. So for a loop, point P to where we're looking at the magnetic field strength, so the loop with the current through it generates our magnetic field at some point P. This distance here, r hat, is always going to be perpendicular to that tiny little bit of dl that we're looking at, and that's going to be true for any point along because we're dealing with a circular, so r is going to be constant no matter how crappy I draw my drawing here. This is always going to be perpendicular, so we can just collapse dl cross r hat into dl. So it allows us to reduce here. Alright, so we need to sum over all of our tiny dl's. And all those tiny dl's will sum up to the circumference of the circle. So we are going to integrate from 0 to 2 pi r. And that's going to give us then and be careful here, we're integrating in terms of L, not in terms of R, which is why I'm just subbing in a 2 pi r and understanding if I evaluated for the 0, it's just going to give me minus 0, so I'm just not going to put that in there. Alright, so that allows me to reduce. And this in the notes may be written as an A rather than an R. Now this is for one loop. If we have multiple loops, we can add in a capital N, where N is the number of loops. Now in this particular case, remember if we're doing a right-hand rule, we are putting our thumb in the direction of the current. So in this case, we're putting it along the path of the loop, and our fingers are going to curl in the direction of the magnetic field. So we have to remember that we can put our fingers back behind the loop, and it can come in or out of the page. So essentially what you end up with, if you're looking at the loop, is all of these loops around the loop. So this is your magnetic field strength. And so they concentrate here at the center, which is why we do this specifically for the center of the loop, because it's going to be strongest here and then weak on the outside. And you can see a picture of this on page 932 in the textbook, which shows you essentially the magnetic field lines looping around the current carrying loop. Alright, so in the notes there is another formula which I'm not going to derive here. There is the derivation in the textbook, but I will give this to you. And this formula is used if you want to find, instead of at the center of the loop, some distance in front of the loop. So I've drawn the loop sideways here. And so if you want to find at some distance x in front of that loop, this would be the formula. So notice very similar to the electric field. How you calculate the electric field depends upon how the charge, in this case the current, is distributed in the system and where you're actually trying to find it in the system. So we saw that with the problem with the sheet being very close to the sheet of charge versus being very far away from the sheet of charge. It matters how the charge is distributed and your distance away from it, how you actually do your calculation. And you can also multiply this by n in order if you have multiple loops. And you can get the formula I derived on the previous page by subbing in x equals 0 if you choose to.